we have to minimize these eddy currents. So there is a method to minimize the eddy currents. So how we can minimize eddy currents? Eddy currents are minimized by using laminations that are separated by insulating material like a lacquer. Actually, the plane of the laminations must be arranged parallel to the magnetic field. Then only that arrangement reduces the strength of the eddy currents. So the efficiency of the devices may increase. Eddy current will generate heat. Okay. So due to that, the efficiency of those electric motor and transformers may reduce. So it is must to minimize these eddy currents. So how we can minimize? With the help of laminations. But how these laminations are prepared? With the help of a material that is lacquer. So the plane of these laminations, they must be placed parallel to the magnetic field and the strength of the eddy current can be reduced. I told you already in the beginning, even though these eddy currents are undesirable, they are used in a few applications. So what are the applications of eddy current? The first application is magnetic braking in trains. So it is automatic braking, magnetic braking in trains. So that means manual operation will not be there. With the help of these eddy currents, this magnetic braking in trains is possible. So how the magnetic braking in trains is possible? Strong electromagnets are placed above the rails in some electrically powered trains. In electrically powered trains, strong electromagnets are placed. When these electromagnets are activated, what will happen? There will be suddenly a change in the flux. You know, according to Faraday's law, when there is a change in the flux, EMF is induced, they further produces currents. Those currents are called as eddy currents. So when the electromagnets are activated, eddy currents are generated and they oppose, according to Lenz's law, they oppose the original cause that produces it. Actually, what is the original cause? The motion of the train. So while the train is moving, electromagnets are activated, currents are generated, and immediately they oppose the motion of the train. This is what magnetic braking in trains. The next application is induction furnace. Induction furnace can be used to produce high temperatures and can be utilized to prepare alloys by melting the metals. Actually, eddy currents that are generated in the metals produce high temperatures. So these high temperatures only used to prepare alloys by melting the metals. So in this way, eddy currents are used in induction furnace. The next application is electric power meters. So in any electric power meter, if you see, there will be a coil and that will be rotating. So actually the eddy currents are induced on that coil. So it is like a disc. So eddy currents are induced in the disc by magnetic fields produced by varying currents in a coil. So there will be a coil. So due to the varying currents in the coil, eddy currents are generated in the disc. These eddy currents rotates that shiny disc in the electric power meters. So in the electric power meters also, these eddy currents are used. These eddy currents only rotate the shiny disc in the electric power meters. These are the applications of eddy currents. The next important topic is self-induction. It's very, very important. So what is self-induction? When a current flows in a coil, magnetic field is set up. If the current passing through the coil changes with time, an induced EMF is set up in the same coil and it opposes the change in the current. This phenomena is known as self-induction. So you can see here a coil. Here, when current is passing, we know when current is passing across this coil, this acts like a magnet. So I can say magnetic field is developed across this coil. Now, When this current is increasing, so current is changing. So according to Oersted's experiment, when there is a change in the current, it acts like a magnet. And magnet means there will be a magnetic field. So there will be magnetic field lines. Current is increasing, so the magnetic field will increase. So the number of magnetic field lines cutting across this coil are increasing. So due to increase in that magnetic field, there will be change in the magnetic flux. According to Oersted's experiment, when there is a change in the magnetic flux, what will happen? EMF is induced. So the EMF that is induced in this, and it further produces current. So when this is happening in the same coil, then that is called as self-induction. That is, when current flows in a coil, it produces the magnetic field, and when there is a change in the magnetic flux in this coil, if EMF is set up in the same coil, then that phenomena is known as self-induction. When there is a change in the flux in a coil, EMF is induced in the same coil, then that phenomena is called as self-induction. Then what is the coefficient of self-induction? This can also be called as self-inductance. Self-inductance or coefficient of self-induction. Actually, we have discussed that when current that is passing through this coil, magnetic flux is developed. So the developed the magnetic flux is depending on the current that is passing through this coil. So how it is depending? It is directly proportional. When there is an increase in the current, flux increases. When there is a decrease in the current, flux decreases. So I can say flux is directly proportional to the current. When we remove this proportionality, we get a constant. That constant here it is L. This L only is called the coefficient of self-induction or self-inductance of the coil. So from this equation, phi B equals to L into I. Now, in order to define this coefficient of self-induction or self-inductance, I am considering I equals to 1 ampere. I is 1 ampere. Then if I substitute that in this equation, we get phi B equals to L. So, the coefficient of self-induction is equals to magnetic flux. So, now we will see how we can define this coefficient of self-induction. See here, there is a coil, current is passing. But the current that is passing through this coil, what we have considered? 1 ampere. So 1 ampere is the current that is passing through this coil. When 1 ampere current that is passing through this coil, what happened? There is a change in the magnetic field which produces the magnetic flux. So flux is directly proportional to that current that is passing through this coil. If you remove this proportionality, we get a constant. So phi B equals to L because the current that is passing through the coil is 1 ampere. So now how we can define the coefficient of self-induction is numerically equal to the magnetic flux linked with this coil. When the magnetic flux that is developed when 1 ampere current that passes through this, that is when 1 ampere current that passes through this, the flux that is produced in the same coil, then that is the coefficient of self-induction or self-inductance. The coefficient of self-induction is numerically equal to flux that is developed in a coil when 1 ampere current that is passing through this coil. So this is the definition of self-inductance or coefficient of self-induction. There is some other definition for coefficient of self-induction. So what is the other definition? We will see. See, when the current is varied, here in this circuit, I told you already, current is increasing, or we can also take current that is decreasing. So when the current is varied, the flux linked with the coil changes. So it produces EMF. We know according to Faraday's law, E equals to minus d phi by dt. So that equation only I am using, E equals to minus d phi by dt. But according to equation 1, the flux that is linked with the coil is depending on the current that is passing through the coil. So phi b equals to Li. Substitute this equation in that equation in place of phi. So if I substitute, what I will get? E equals to minus d by dt of Li. So here differentiate this equation. If I differentiate, what I will get? Minus L di by dt. So consider this as equation number 2. In order to define the coefficient of self-induction, now I am considering di by dt equals to 1 ampere. Di by dt is what? The rate of change of current. It's not current, it is the rate of change of current. Now, the rate of change of current is 1 ampere. When this is 1 ampere in this equation, what we can write? E equals to minus L. So if I take out this minus, because it anyhow it indicates the direction of EMF. Magnitude of EMF is L only. So the self-inductance is equals to EMF when the rate of change of current is unity. That is only the definition for the coefficient of self-induction. So how we can define? The coefficient of self-induction or self-inductance is numerically equal to the induced EMF in the coil when the rate of change of current in that coil is unity, in the same coil. Okay, here the rate of change of current is not in some other coil. You can see here, current is changing in this coil. So EMF is generated in the same coil. That is why this is called as same, in the same coil. That is why self-induction. So here from this equation, self-inductance is EMF that is developed in a coil when the change in the current, the rate of change of current is unity in that same coil. Then there is some other definition also. So what is that definition in order to see these equations? So see here what we have discussed. Current in the coil is switched on. So current is increasing. So what will happen when there is an increase in the current? So see here, when there is an increase in the current, there will be a change in the magnetic flux in this coil only. So when there is a change in the magnetic flux, EMF is generated in this coil. And what does that EMF do? It opposes according to Lenz's law, it opposes the original cause that produces it. So this EMF, it will not allow the current to increase. Actually, because of this increase in the current only, EMF is generated. That is the cause. Increase in the current only is the cause for the EMF to develop. But this EMF, what does it do after developing in this coil? It will not allow the further increase in the current. It tries to decrease the current. For example, if there is a decrease in the current, whether there is an increase or decrease in the current, we can say there is a change in the current. So when there is a change in the current in a coil, there is a change in the flux that is developed in this coil, and due to that EMF is developed in the same coil. That is self-induction. So when there is a decrease in the current, EMF is generated, and according to Lenz's law, that EMF opposes the original cause. What is the original cause here in this case? Decrease in the current. So that tries to increase. So in this case, there is an increase in the current. So the developed EMF try to decrease the current. Here there is a decrease in the current. So the developed EMF try to increase the current. So here current, initially battery is not there, then current is 0. Now battery is switched on, then current is increasing. Slowly current is increasing. Change in the magnetic flux, EMF is generated. So it tries to oppose the increase in the current. But anyhow the current has to increase to its maximum value. So in order to increase to its maximum value, it has to do some amount of work against this back EMF. EMF is generated. So then it is not allowing this current to increase. But current, it has to increase to its maximum value. So what does it do? It has to increase. So it will do some amount of work against the back EMF. So that amount of work that is said to be done is dW equals to EI dt. This negative sign you can write, or only magnitude also you can take, because this negative sign indicates that work that is said to be done against this EMF. So dW equals to EI dt. In order to increase the current to small amount of work that is said to be done. But in order to increase the current to its maximum value, large amount of work that is said to be done. That can be obtained by integrating this equation. Before integrating, substitute the value of E from this equation. If I substitute, what I will get? dW equals to L di by dt. In place of E, I wrote L di by dt into I dt. If you are getting confusion with this negative sign, you just forget about that, because it anyhow indicates the direction. I have taken only the magnitude. So dW equals to EI dt. Now we are substituting E value from this equation to in this equation. So dW equals to L di by dt into I dt. So here this dt will get cancelled. dW equals to L I di you will get. That is what you can see in the next equation. dW is L I di. But we need to get the total amount of work in order to increase the current from 0 to its maximum value. That means we need to integrate this equation. So if I integrate this equation within the limits 0 and I naught, as the current has to increase from 0 to maximum value, the lower limit will be 0 and the upper limit will be maximum value, which is I naught. So integration of dW is W. L is the coefficient of self-induction, which is constant. So we cannot integrate right outside the integration. Integration 0 to I naught. What are the remaining terms? I di. Integration of I di is I square by 2. Integration of I di is I square by 2. But we also have to substitute the limits. First upper limit you will substitute. So in place of I, what I will get? I naught square by 2. If I substitute 0, lower limit, that is anyhow 0 only. So the total amount of work that is said to be done is, L is here. Integration of this is I square by 2. That means 1 by 2 I square. But I substituted the limit, so I naught square you will get. So this is the expression for magnetic field energy. Because the amount of work that is said to be done will store in the form of energy. That energy here, it is called magnetic field energy. Then from this equation also, I can define the self-inductance. How we can define the self-inductance, you see. Here I naught is there, and now I am considering that I naught as 1 ampere. If this I naught is 1 ampere, then what I will get? L equals to, this I naught is 1. So W equals to what you will get first, you see. W equals to 1 by 2 L. Because I naught is 1. 1 square also 1. So 1 by 2 L. L equals to what I will get? 2 W. So what I can write the definition of this coefficient of self-induction? The coefficient of self-induction is, if you see the equation, you can write. The coefficient of self-induction is twice the amount of work that is said to be done when 1 ampere current that is induced in a coil. The coefficient of self-induction is twice the amount of work that is said to be done in a coil when 1 ampere current, or you can say here the current is increasing from 0 to 1 ampere, because I naught is 1 ampere, no. So the coefficient of self-induction is twice the amount of work done in order to increase the current from 0 to 1 ampere in the same coil. So here we got one expression, that is W equals to half L I naught square. From this equation also we can define the coefficient of self-induction. The coefficient of self-induction, in order to define, consider this I naught as 1 ampere. What is I naught? The maximum current. Current that is increased from 0 to I naught, no? So that consider it as 1 ampere. So if I take I naught as 1 ampere, we get L as 2W. So from this equation, the self-inductance or coefficient of self-induction is twice the amount of work done. Why the work that is said to be done? In order to increase the current from 0 to 1 ampere. So I can say coefficient of self-induction is twice the amount of work done in a coil to increase the current from 0 to 1 ampere in the same coil. That is coefficient of self-induction and the concept of self-induction. Then the next topic is self-inductance of a long solenoid. So how we can calculate the self-inductance of a long solenoid, that we are going to derive. So in order to derive that self-inductance of a long solenoid, consider a long solenoid of length L, area of cross section A. And let us also consider there are n number of turns per unit length. Capital N is total number of turns. The small n is number of turns per unit length. Let us also consider I is the current that is passing through the solenoid. So I is the current that is passing through the solenoid means I is the current that is passing through each and every turn of the solenoid. Now, what is the magnetic field inside the solenoid? That is B equals to mu naught Ni. This we have already discussed. In moving charges and magnetism, the magnetic field due to a solenoid is B equals to mu naught Ni. But now we want magnetic flux in order to calculate the self-inductance. So we know flux phi B is B into A, BA. B is what? Mu naught Ni. So substitute this equation in this equation. I get phi B equals to mu naught Ni into A. So if there is only one turn, then we get mu naught Nia. But if there are n number of turns, we get n phi B, that is equals to mu naught Nia into n. But this capital N is what? N into L, because n is total number of turns. Small n is number of turns per unit length. So we can write small n as total number of turns per length. So small n is capital N by L, but capital N is N into L. So this is n phi B, that is the flux linked with n number of turns, which is mu naught Nianl. So here n into n is n square. So we get the total flux due to n number of turns in a solenoid is mu naught n square IAL. So what is self-inductance of a solenoid? We know the expression for self-inductance of a solenoid. Okay. Actually, we know the self-inductance, that is L equals to phi B by I. Self-inductance is phi B by I. According to this equation, self-inductance L equals to phi B by I. That equation I am going to use here. So here we got already, due to the n number of turns, phi B is mu naught n square IAL by I is self-inductance. So the self-inductance of a solenoid is L equals to mu naught n square IAL by I. So this I will get cancelled. Then the self-inductance of the solenoid is mu naught n square AL. The self-inductance of the coil depends on the geometry of the coil and the permeability of the medium.